Hi guys, welcome to the next section, Support Vector Machines. In this section, we will start with support vector machine working principles. We will then move to kernel functions. Finally, we will see SVM multi-label classifier. Now, we move on to the first video of this section that deals with support vector machines working principles. In this video, we're going to take a look at support vector machines that are mainly classified into three types based on their working principles. First is the maximum margin classifiers. Next one is the support vector classifiers. The last one is support vector machines. Let's move to the first type, that is maximum margin classifier. People usually generalize support vector machines with maximum margin classifiers. There is much more to present in SVMs compared to maximum margin classifier. It is feasible to draw infinite hyperplanes to classify the same set of data. But the question is, which one to consider as an ideal hyperplane? The maximum margin classifier provides an answer to that, the hyperplane with the maximum margin of separation width. Let's see what are hyperplanes. In n-dimensional space, a hyperplane is a flat affine subspace of dimension n-1. This means in two-dimensional space, the hyperplane is a straight line which separates the two-dimensional space into two halves. Here's the equation for hyperplane. There are regions above and below as well. This means observations can fall in either of the regions, that is, region greater than 0 or region smaller than 0, also called the region of classes. The mathematical representation of the maximum margin classifier is like this. Constraint 2 ensures that observations will be on the correct side of the hyperplane by taking the product of coefficients with x variables and finally with a class variable indicator. In this diagram, we can draw infinite separate hyperplanes to separate the two classes, that is blue and red. The maximum margin classifier attempts to fit the widest slab that maximizes the margin between positive and negative hyperplanes between two classes and the observations touching both the positive and negative hyperplanes called support vectors. Another type of SVM is support vector classifiers. They are an extended version of maximum margin classifiers in which some violations are tolerated for non-separable cases in order to create the best fit, even with slight errors within the threshold limit. In real-life scenarios, we hardly find any data with purely separable classes. Most of the classes have a few or more observations in overlapping classes. The mathematical representation of the support vector classifier is like this. There is a slight correction to the constraints to accommodate error terms. In constraint 3, the C value is a non-negative tuning parameter to either accommodate more or fewer overall errors in the model. Having a high value of C will lead to a more robust model, whereas a lower value creates the flexible model due to less violation of error terms. C value would be a tuning parameter, as is usual with all machine learning models. The impact of changing the C value on margins is shown in this diagram. With the high value of C, the model would be more tolerating and also have space for violations in the left diagram, whereas with the lower value of C, no scope for accepting violations leads to a reduction in margin width. C is a tuning parameter in support vector classifiers. The third type is support vector machines. They are used when the decision boundary is non-linear and would not be separable with support vector classifiers, whatever the cost function is. The diagram illustrates the non-linearly separable cases for both one dimension and two dimensions. It is apparent that we cannot classify using support vector classifiers, whatever the cost value is. Hence, we need to use another way of handling the data, called the kernel trick, using the kernel function to work with non-linearly separable data. A polynomial kernel with degree 2 has been applied in transforming the data from one-dimensional to two-dimensional data. By doing so, the data becomes linearly separable in higher dimensions. In the left diagram, different classes, that is red and blue classes, are plotted on x based to 1 only, whereas after applying degree 2, we now have two dimensions, x based to 1 and x based to 1 raised to 2. The degree of the polynomial kernel is a tuning parameter. We need to tune them with various values to check where higher accuracies are possible with the model. Whereas, in the two-dimensional case, the kernel trick is applied as below with the polynomial kernel with degree 2. It seems that observations have been classified successfully using a linear plane after projecting the data into higher dimensions. In this video, we have learned support vector machine working principle.